Good morning, everyone. My name is Ryan Evans, and I have the pleasure of speaking with everyone here this morning to give an introduction to energy modeling as part of the Better Buildings Bootcamp provided by Sustainable Buildings Canada. So thank you, everyone, for joining. It's exciting to see, well, unfortunately, I can't see you, but it's awesome to have everyone showing interest in this line of work. This is something that my team and I take very seriously, and we're excited to be sharing a little bit of what we do with you. So here we go. Energy modeling. I've been doing energy modeling now back since 2005. I started out doing home energy modeling on single family homes, and then graduated to larger commercial buildings. And we work on some buildings as high as almost 100 stories. The largest building we worked on was about 85, 90 stories. So it's really cool to see the progress of the energy modeling industry over the last 15 to 20 years. And so my understanding is that the participants in the boot camp are coming from a wide array of disciplines in your studies. So what I wanted to do is I wanted to give a basic introduction into what is building energy modeling, and hopefully during the Q&A you'll ask some questions if there was something particular that that you didn't catch or didn't understand. But I did try to make the presentation as general as possible in terms that are not really industry specific terms, but in a way that everyone hopefully will be able to understand. So building energy modeling is the practice of creating digital representations of a building using a specialized software. And the objective is to predict the energy performance of the building, and then comparing that to a baseline. And so it all depends on what type of project we're going to be working on, whether it's going to be an existing building or a new construction. That baseline is going to change, and I'll speak to that in a couple of minutes. Whole building energy models is the creation of the entire building from the outside envelope all the way down to the small lighting fixtures and electrical plugs that we plug our appliances and our electronics. So we try to capture anything and everything that will be using energy, whether it's electricity, whether it's natural gas, or any other carbon fuels. Anything that's going to be considered an energy user, we're trying to capture that within the scope of our building energy model. So for example, I mentioned building envelope assemblies. So this will include your exterior walls, this will include your roofs, this will include floors, windows, doors. So anything that's going to be the outside skin of the building. Electrical equipment. So this is, you're thinking of lighting, you're thinking of appliances, your electronics, your phones, your computers, your monitors, your televisions, your sound systems, what have you. You also have in more commercial buildings, you'll have elevators and escalators. So these are all type of electrical equipment that we have in a building. And then there's the mechanical equipment, which is meant for the conditioning of the environment. So it's the heating, the equipment used for heating, it's the equipment used for cooling, the fans for circulating air throughout the building, and the various components that make up each one of those systems. If, for example, a boiler is used to heat water, that circulates for space heating. You have a chiller that's used to cool water, and it's circulated for space cooling. Cooling towers are part of the cooling plant system, and that's for use for heat rejection as part of the cooling system, etc. The analysis that we conduct using building energy models are mainly used to estimate the performance benefit from either improving a single system at a time or multiple systems. So when we talk about energy modeling and specialized software, I've kind of put together a little slide here of the various softwares that are being used by ourselves here at Evan Engineering, as well as our colleagues in industry. So we have eQuest is a familiar one that's being used in school. It's been around for quite some time. That actually runs on the DO2 engine, and that's the actual simulating software. When I started out back in 2005. Hot 2000 was the energy model that I used, and it's still used today in residential applications. There's a brand new green program that the federal government just launched a few months ago for homeowners and looking to go get some grant money on home improvements. And this is a software that's being used by those home energy auditors. We have Energy Plus, which is a more sophisticated modeling software. It's actually a text-based, so it can be really challenging to use. So we have a few front ends. This is Symergy and Open Studio. These are both front ends that run on Energy Plus. We have IES, Virtual Environment. This is another really sophisticated software that we use in-house here at EVNA. And it's great because it not only does energy, but it also does some solar analysis. It does thermal analysis, and it's a great software for us to be doing advanced energy modeling on building systems. Carrier has their own hourly analysis program. It's called HAP. Train, who's Carrier and Train are both manufacturers of mechanical equipment. They have their T700. There's Design Builder and Transys. So these are all softwares that have been used. And lastly, NRCan created CanQuest, which is a Canadian version of eQuest. So as you can see, there's not just one software that people use. There's many different options depending on what type of analysis that you're looking to conduct. Here at EVNA, we use IES, we use Energy Plus, and we use eQuest. We're familiar with HAP and DOE 2, and we also use a little bit of Hot 2000. We're not users of the software here at the moment. So this, I want to give you kind of a screenshot of what does an energy modeling software look like. So we usually build it up in different system components. So the way I kind of broke it down in the first slide, we focus on building the building envelope first. Then we look at doing the electrical systems and the schedules. What are the occupancy loads looking like? How many people are going to be in a building for how long during the day, because these all influence the energy use in a building. And then afterwards, we go and we start putting together the different mechanical systems. So this screenshot here, this is in Symergy, and this is where the modeler will be building up the envelope. They're defining the walls and the windows and the roofing systems, as well as any below grade basement levels as well. This is a screenshot from eQuest, and this is in the airside mechanical systems tab, and this is where we build up all the different mechanical equipment, which you'll be seeing in more detail on Thursday during the workshop with one of my team members, Sean Sergi. And here we're putting together a DX cooling coil with a gas-fired furnace as an example of one of these airside systems. This is a screenshot from IES, and this is one of their solar analyses, one of the modules that they have, and evaluating the impact of the solar heat gain from the sun at the various stages of the day. So as you can see, there's quite a few different cool things that we can do with building energy modeling today. There's been a lot of evolution over the last few years. This is another screenshot from IES, and this is showing us how we actually can build up all the various components of the mechanical system. This is another screenshot again. It's showing here how we're combining boilers with your cooling tower, and then how we're connecting them to the loads and the different various coils within the building. So with some of the more sophisticated software, specifically IES and Energy Plus, the level of detail that the building model can get can be very granular, which there's pros and cons to that. Just means that you need to have a lot more information in the building with these more sophisticated software. So often what we start off with, if we're doing a very simple analysis, sometimes we'll start using a simpler tool because there's just the way the calculations get done. We don't have enough information to do a very detailed model, but as we progress in the various stages of the design, we then can shift over to a more advanced software, and we begin getting higher quality results in our analyses. So when do we use energy modeling? There's a few scenarios in which we'll use energy modeling, and today across pretty much most of our provinces now, energy modeling is a requirement for new construction. As any new building that's going for a building permit, and before it gets the approval from the municipality to be built, needs to demonstrate that it's going to comply with the energy codes that are in force. We have a national energy code in Canada. It's called the National Energy Code for Buildings, and it's the 2017 version, also referred to as the NECB 2017. This is something that my team and I work with on a daily basis to help our clients, whether it be condo developers or multi-res apartment developers or office buildings, universities such as the U of T, anybody who's looking to build a new building or a new addition to an existing building, they must comply with energy codes, and we're there to help the design team, be it the architect, the electrical and mechanical engineers, achieve those targets and objectives. Energy modeling is also used in the existing building sector, and in that sector, we can use energy modeling, although it's not very common because there's not a lot of people who do energy modeling. For energy audits, you can create an energy model to help do your calculations in lieu of doing manual base principle engineering calculations. From there, you can start using an energy model to do system retrofits. So you can analyze a particular a single system within a building. Even though you've done a whole energy model, you can just really zone in and say, hey, we want to change the lights in our building. What is the impact of that? And everything else just stays the same. Or we can look at doing a deep energy retrofit, and that's looking at achieving a higher percent savings, closer to about a 50% relative to our baseline. So lots of current and future potential use of energy modeling within the existing building sector. There's also a new form of using energy modeling with existing buildings as well as new construction, and that's the concept of ongoing commissioning. And this is continuous monitoring and optimization of a building. And one approach is to create an energy model that is a digital twin of the building. And by digital twin means that we're feeding in real-time data from utility meters and from sub-meters throughout the building, and we're doing constant real-time calibration on the model so that in real time it represents what the building, how it's operating and how it's using energy. This becomes a really cool tool for the building operators and the decision makers of a project to then run various scenarios and to see where is the money best spent to achieve the performance objectives that they're trying to achieve. Lastly, future proofing is becoming something of interest to a lot of stakeholders and projects, and that's through the use of future weather predictions. U of T actually has future weather predictions for an array of years into the future. And this is something that is used to kind of give us a little bit of insight onto how our building is going to be performing today versus in the future when the effects of climate change are coming into play. So I just wanted to give a little side-by-side comparison. Most of the work that we tend to do today is in the new construction and the existing building sector. So I just want to give you some terms that you'll be hearing a lot on Thursday during the workshop. Our particular project that we're working on for the U of T is an existing building. So I'll just start with that, but then I also want to give you just a little comparison of what that would look like in a new construction analysis. So for an existing building, we're doing a relative analysis. That means we're comparing a proposed scenario to a baseline. The baseline building is a representative model of the existing building as it is today, and we calibrate that to an improved accuracy using historical utility data. The proposed building is created from the baseline building, and what we do is we incorporate the energy conservation measures, the changes in the system improvements that we want to implement into the building, and then through that relative analysis and the comparison, we're able to see what is the performance gain of those various measures. We can do them incrementally, which gives us a little bit more visibility, so one measure at a time. But then you also need to do an analysis of the aggregate of your measures. So I'll give a little bit of an example to that. If we're interested in improving the lighting system and let's say the heating system, okay, we're going to change the boilers. If we do an analysis just on the lighting system, it's not going to really take into account what are the impacts on the other systems. When we improve lighting, let's say we're taking it from an old, let's imagine that we have an older building and it still has fluorescent lighting. It hasn't been converted to an LED system yet. Those fluorescent light ballasts actually produce heat. So when we start retrofitting those lighting systems to a more energy efficient LED system, they'll use a little bit less energy, and consequently you produce less heat that actually aids in the space heating in the building. So by having less heat generated by your lighting system, it actually influences positively on your cooling system because there's less of a cooling load. However, it has a slight negative impact on your heating system because now your heating system has to make up that difference. So another reason why we use whole building energy modeling is that we want to account for the interdependencies between systems. If we make an improvement to the envelope and we add insulation to the exterior wall and the roof, well, that's going to reduce the thermal load of the building, the amount of energy required just to keep your space at a comfortable temperature when it's cold outside or when it's hot outside. So you don't want to just look at the envelope by itself under a magnifying glass and then not account for what's going to be happening with some of your other systems. When you make an envelope improvement, and you make it better, you're essentially putting less of a load on your heating and your cooling system, and that usually impacts it in such a way where now you can size your equipment. You can put in smaller pieces of equipment to achieve the same performance levels. In new construction, we still do a relative analysis. The terminologies change a little bit and the approaches change a little bit. So in a new construction, we're looking at building something brand new that doesn't exist. And we don't have an existing baseline with historical utility data to compare it against. So the practice for us to validate and verify if we're building an energy performing building is to compare the proposed building to a reference building, which in itself is a code compliant reference building. And what I mean by that is if we were to build a building and doing nothing more than the bare minimum requirements to meet our building code performance requirements, this is essentially what that reference building represents. So the way we go about doing a new construction analysis is that we will create the proposed building first, and that is the representative model of the new building that we're looking to build. And we're basing those model input on the design team's drawing. So that's the enclosure, the envelope enclosure details from the architect, and the mechanical and electrical details from the engineers. We're not looking at structural elements. We're not looking at the landscaping. So there's a lot of other designers that are part of a design team when we build a new building. But the three key designers that we work with on a regular basis that have a lot of influence on energy use is the architect, the mechanical, and the electrical engineer. Once we've created our proposed building, it's from the proposed building that we go and we create the reference building. So that's the key difference in new construction versus existing building. In an existing building, we have our baseline that's representative of our building with historical data, and then we go and create our proposed building from that baseline. It's the inverse in new construction. And so the reference building is being created from the proposed building, and we're changing certain key input of the system. So let's call it the system efficiencies, the lighting power allowances. So the amount, and we're dialing those input back equal to what would be prescribed as a minimum requirement in the code. So now our reference building will represent the code, and the proposed building represents our design, And the relative analysis is the reference minus the proposed, and that gives us our savings. And we're trying, in certain areas, there's performance targets such as we need to do 15% better than the reference building. So that means our proposed building has to be 15% less energy than our reference building. So with regards to our project that the charrette on Thursday is going to focus on, we have the health science building. So this is located in Toronto. With regards to our climate zone in modeling, we look at the location of the building and the influence of the climate, because that's going to have an impact on the heating and cooling loads. So we're located in Toronto, and that's climate zone 5 according to our National Energy Code, the NECB. We have a 7-story building. It's approximately 15,672 square meters in area. It's a mixed-use institutional building. It's got offices, it's got classrooms, and it was built in 1957. And so here's a little aerial view of that. So Sean's been working really hard in preparation for Thursday's charrette. So this is kind of a little bit of an insight of what that building looks like within our model. So what we want to do is we want to try to create a representative model of the building, and we're going to be calibrating that based on the utility data. And from there, we're going to be looking at various system improvements proposed by the subject matter experts. And then at the end of the workshop, we're going to be verifying what potential of improvement do we have, incorporating some of the measures that are of most interest to the project stakeholders. I mentioned calibration. So when we talk about a calibration model, and this is an exercise that's going to be done for our charrette, we're looking at taking historical utility data. So here I have some electricity. This is from a separate project. So we have electricity use, and I have 1, 2, 3, 4, 5, 6 years of historical data. And I've plotted them here in a chart. And what we've done is, after creating the model and doing the calibrations, I'm trying to get this dotted green line to be within my range so that I feel comfortable. And there's a few formulas that we follow to verify that we fall within a tolerance level that's acceptable, plus or minus 10% from what we're trying to achieve. And this here, once I achieve this calibration, I have a level of comfort to say that my model is now a relatively decent representation of the existing building. And from here, when I start making system changes, the improvements that we're going to get, this would be pretty close to what we should be seeing in real life at the downstream of the utility meter. So we do the calibration on the electricity, and we do the calibration on the gas. Now, one thing to note when we're doing calibration is not every year is going to be the same. Some years the weather is going to be warmer. Some years it's going to be cooler. Some years things are going on and there's system improvements being done. And in this particular project, we noticed that in the gas system, which is used to heat the hot water and the fresh air in this particular building, there's no space heating being done by gas. That's the reason why we see the electricity is really high here in the winter, and then it drops, and it's got a little bit of a bump from the cooling here in the summer, and it drops again in the fall. May and September, these are considered our shoulder seasons, and then it upticks back up here in the fall, October through December, as the weather gets colder. So this is an indication that this is an electrically heated building. Here we don't have a lot of gas use, so that's because it's really just domestic hot water for your showers and your kitchens and your washrooms. And this would be an anomaly here that we're saying in the year 2016. So we try to get at least 4 to 5 years of utility data in the event that we do have a year that is an anomaly, and we can pull that out so that it's not going to skew the results of our model. This year was not really representative. So 1 out of 6, and we're seeing that 1 year is the anomaly, we can pull it out. And the objective is for us to get a comparison between the reference and the proposed. So this would be in a new construction, the reference being the code compliant building and the proposed being our design. If it was for U of T, the reference building is going to be referred, this would be the baseline building, and then this would be our proposed building. So the terminology, the reason why I wanted to speak to that today is that you'll start seeing baseline and reference are synonymous, but baseline is used in an existing building, and whereas a reference building is being used in the new construction. So here we're looking at the various systems. We're getting the total energy use, which is around 920,000 equivalent kilowatt hours. And we use equivalent kilowatt hours as a unit of measure. And this accounts for electricity and natural gas. And we try to put it all on one unit of measure to give us a ballpark. When you start using different units, there's natural gas has different heat content and energy content than compared to a unit of electricity, kilowatt hour. So by putting them all in the same unit, this allows us to visually have a good representation of what the savings are going to be. An alternative to an equivalent kilowatt hour would be using joules and gigajoules as a unit of energy. So here we have our reference showing that we're around 129,000 equivalent kilowatt hours, and our proposed building was sitting at around 778. And again, this was a new construction, so a graph from one of our new construction projects. So we're showing a savings around 141,680 kilowatt hours, and that's a percent savings about 15.4%. So this would be great for a sustainable buildings project. If it was going for a savings by design incentive with Enbridge, as an example, this would meet the minimum threshold requirement, which is a 15% better than code. So I'm getting close to the end of my allotment in time here. So I got one more slide to show you. The future proofing of buildings. So this is where we're looking at those future weather files. And what we're doing is we're looking at the heating and cooling loads. And so we're seeing in 2021, using our normalized weather files of today's weather, we're seeing what the loads would look like. And then in 2040, we're seeing what the cooling load is going to look like and what the heating load is going to look like. So we're seeing that it's getting a little bit warmer on the heating side. Hence, it's not going to be as cold during the wintertime. However, we are seeing a much bigger uptick in the cooling season. So that means summers are going to get really hot. So this is something that we want to take into consideration, that buildings being designed today without air conditioning is really a big no-no, because that's putting the health and comfort of the occupants at a significant risk. Maybe not today, but definitely in about 20 years from now. So thank you very much. I got finished just in time. I got a couple minutes left. Thank you for your participation. We have our gamification code right here for a presentation. It's called Project Runway Building Edition. And I look forward to hearing any questions you may have in the Q&A session right after this. Thank you very much.